my pleasure to introduce the first speaker of the day, Tero Heikkilä. So he will talk about superconductor ferromagnet system out of equilibrium. So please.
Thank you, Francesco. So good morning, everyone, and thanks for coming, I guess almost all of you, to this morning session. This is an hour talk, so it's boring to listen an hour, the single speaker, so please interrupt me during the talk. And if nobody else interrupts, then Sebas should do it, or Jason. Right. Okay, good. So this is work that was done together with, among others, Sebas Bergeret and his former student, Asier, who visited me actually in Helsinki when I was there. And basically the collaboration for this started from that visit. And then later on it expanded into many things, which we then, I mean, not only our work, but also related work we reviewed in this paper that was submitted to Reviews of Modern Physics last June. Yes. Well, okay, the topic of the conference relates to superconductivity and magnetism, so that's also what I'm going to talk about. So I'm going to basically ask what happens when we marry these two interacting systems. And superconductivity, in my case, actually, for me, only means almost only means the density of states. So I'm not talking about supercurrent itself, but of course there are some coherent effects still related to superconductivity. Magnetism means basically two things. So one is this sort of basically the spin polarized Fermi surface, and the other one is the exchange field related with magnetism. Now, my title contained the word out of equilibrium. So, whereas I would guess that the majority of the work on superconductor ferromagnet systems has been done in equilibrium, on equilibrium properties, looking at the proximity effect from superconductors to ferromagnets, sometimes vice versa. These equilibrium effects, they usually show up at length scales related with coherence lengths. So in the superconducting cases, coherence lengths are typically between 10 to 200 nanometers or so. Let's say the aluminum is the 200 nanometers, then for higher TC you get smaller coherence lengths. In the magnetic case, if you look at the just the penetration of the singlet correlations, you have the magnetic coherence length, which is the few nanometers at max, depending on the magnet. Now, this is in contrast to out of equilibrium effects, which are related with, let's say, looking at what happens to charge, spin, heat transport, and then in this case, the relevant length scale is rather the relaxation length. Okay, for charge, let's say the charge is usually conserved, so there might not be even a relaxation length. There is a relaxation length for charge imbalance. This is typically very long, but the other length scales are sort of typically the inelastic scattering lengths, which at low temperatures below 1 Kelvin, where we are interested in mostly because of superconductivity, these length scales are up to several micrometers. And then there is also for spin effects, there must be the spin flip relaxation length, which is typically hundreds of nanometers in metals.
Hey, Tero, since you want to be interrupted,
yes.
LSF can be a lot shorter than that in some ferromagnets.
Yeah, okay. In ferromagnets, that's true. Yeah, so I'm going to concentrate, thanks Norman for this, I will be mostly concentrating on what happens inside the superconductor. Okay, our work started from a bunch of experiments in some 5-6 years ago, studying spin transport in superconductors. And so here's an example of experiments. There were actually related experiments before this, but these were the ones which motivated us to do this study. So this is an experiment by the group in Karlsruhe. What they studied was set up like this. They had an aluminum wire superconductor connected to a series of ferromagnets. And what they did was that they sort of injected a current on this loop, and then they measured a current on this loop. So this was a non-local measurement. So the idea was basically to study how the spin relaxes into the aluminum. So this was a spin injection experiment. And what they did was that they measured this non-local conductance, which is basically just the derivative of this detected current versus the injection voltage. And they put this detector at different distances from the injector. Okay. And what they found out that was a rather large signal, well, typically requiring a voltage which was above the superconducting gap. And the decay scale of the signal that was obtained from this distance-dependent measurements could be inferred to be several micrometers. Okay, and this was a kind of a mystery at that point, because basically it was 10 times larger than the spin flip relaxation length in the normal state. Similar kind of experiments were done by Marco Aprides' group, 2013. And with quite similar results. Well, there was also another experiment by Stuart Parkin measuring actually sort of longer spin relaxation times in these experiments. Now, why is this strange? Well, you would assume that superconductivity, of course, does something on the spin relaxation. Well, I told you already that the spin relaxation length in the normal state, for example, in that aluminum that was measured, was of the order of 300 nanometers. The effect of superconductivity had been evaluated before on the spin relaxation length. This was work by Morten and Beltic, 2004. Now, in the case of in normal metals, it doesn't actually matter what causes the spin relaxation. It could be spin flip scattering or spin orbit scattering. They basically work in the same way. In the superconducting case, they work slightly differently, so that the spin orbit scattering should result roughly the same spin relaxation length as in the superconducting state as in the normal state, whereas the spin flip scattering should actually result to a shorter relaxation length because of some coherence effects. So this basically meant that in any case, sort of one should not get the observed length, which was much longer than observed.
So just to
yes.
specify, the spin flip is the flipping of the spin by a magnetic impurity.
Exactly. Yes.
And spin orbit is the precession until it.
Yeah. This is let's say isotropic spin orbit term that is usually present in any material. So, for example, in aluminum, it's a spin flip that matters, and sorry, this one. And in niobium, which is a heavier material, the spin orbit usually is the dominant one.
So qualitatively, can you explain why in superconductivity the spin flip is much longer length than in a normal state? It's because you're screening the magnetic impurity?
No, I mean it should be much shorter. Okay, it should be much shorter in the superconducting case, but the observation was that it was 10 times longer. Okay, and this was the mystery that I'm trying to explain now during the talk.
Should be shorter? What's the reason?
So basically, okay, so they measure a signal, spin signal here.
I get this, but you expect the spin flip length to be shorter in the superconductor than in a normal metal. Can you explain very shortly why?
These theoretical predictions.
Yeah, the work of Morten and Beltic.
This is the work of Morten and Beltic. Basically, okay. So I mean, you can calculate it. So you can calculate this collision integral for spin flip scattering, and then you look at the coherence effects on this, and basically this is the result. So.
Physical mechanism behind these predictions, or qualitative?
Like hand waving?
Yeah. Yes. Okay. There is. So you have to first look at the spin relaxation time, which I think becomes shorter. Yeah. Okay. Why is that? Okay. I cannot answer immediately. Basically, it comes out of the equations, but there is a physical mechanism, of course. So but I cannot tell. I mean, I can think about it after that. But anyway, I mean, whatever it is, it will give you at most a length scale which is of the same order as in the normal metal. Okay, and this was against the observation. So at first we didn't actually understand at all these experiments, but then okay. So there was one additional piece of information a couple of years later. What was that they The same group measured these spin injection experiments in systems where the aluminum was next to a ferromagnetic insulator. Okay, and they got essentially similar type of results in this case. So the ferromagnetic insulator was giving a magnetic proximity effect to the aluminum, and they still studied what happened to the spin signal. Okay, and roughly similar happened. Okay, so we set up sort of looking at this theory for this experiment, and we kind of divided. Okay, this is kind of the in retrospect we can tell that we divided our task to three parts. First, well, we need to understand such a kind of ferromagnetic superconductor that happens, for example, what happens in this case where you have the superconductor on top of the ferromagnetic insulator. Okay, then we need to describe what happens exactly at the interface between this injecting ferromagnet and the superconductor, or the ferromagnetic superconductor, which is basically giving just boundary conditions for our kinetic model. And then the third task is to find the kinetic equations inside the superconductor. It turns out that actually, once we did this, we found some new interesting results, which I'm about to tell you. Okay, I give a few flashes of the theory, theoretical formulation of this problem. I always indicate this with this acronym D and FU. Details not needed for understanding of the main of the talk, but I try to kind of give you an idea how we do the calculation. So basically, we do quasi-classical Green's function theory. So we look at both in equilibrium, out of equilibrium effects. So the Green's function in question is a Keldysh Green's function, contains retarded advanced parts, which describe basically the spectrum, which are related with the equilibrium effects, and then the Keldysh parts, which is basically the non-equilibrium, describes the non-equilibrium part. In our case, since we are interested in both spin and superconductivity, these matrices, these are here matrices in both spin and Nambu space. So they are basically 4x4 matrices. And you have already seen the Usadal equation in this meeting several times. So we can write the Usadal equation for this, since typically these systems that we are studying are in the diffusive limit. They are disordered. Okay. So this Green's function satisfies this equation, and then basically what we need to add here are the relevant parts describing our setup. So besides just the energy, which is the Fourier transform of the time derivative, so this term here is the exchange field that we might be having in the system, and this is the superconducting pair potential, which satisfies a self-consistency equation. By the way, we don't usually need to solve the self-consistency equation as such, except in the next example that I will show in a moment. And then we need to include all kinds of scattering effects which are encoded in the self-energies. So here we have both elastic and inelastic scatterings, and those related with spin orbit, spin flip terms, and then some inelastic terms like electron-electron, electron-phonon. Okay. Now, first task was to study what happens to the superconductor next to this ferromagnetic insulator. And what we just assume is that, let's assume that first that it's a bulk superconductor, so we can forget about all gradients, and just include this exchange field term and the spin relaxation terms. And then we study this self-consistency equation in equilibrium. So basically, we just solve this. We can solve it numerically if we wish. Actually, in general, you have to solve it numerically. And then you plug it into the self-consistency equation, you solve for delta. Okay. Okay, so these are different parts of the Green's function that you get in the process as a function of energy, but it doesn't matter too much. Okay, so what you get is basically something that was known already since the 1960s. So what you can study is a superconductor in the presence of the exchange field. There are two ways to realize this. It's either this ferromagnetic insulator next to the superconductor inducing a magnetic proximity effect that was also discussed yesterday by Jagadish Moidara, or the Zeeman effect of an applied magnetic field, which is in plane. Okay, And what you get basically is here is the superconducting gap versus the exchange field. Okay. And what you get at low temperatures is this curve, where you have a branch which has multi-valued delta. But basically what you see is that eventually, by increasing the exchange field, you kill superconductivity with large exchange fields. But before you do this, basically you almost do nothing to the delta. Okay. So this is physics that was studied already in the 1960s, first by Chandrasekhar and Kloxton. And there are also this interesting Larkinov-Shingal-Fulde-Ferrell behavior that happens roughly there. Okay. In my talk, I will be mostly in this parameter regime of this red circle. So I'm assuming that almost nothing happens to superconductivity, to delta. Okay. But now you can also study what happens to density of states. Okay. This is 1970s physics. So this is the BCS density of states without exchange field. If you add an exchange field, basically you, without spin relaxation, what you get is that you just have two shifted copies of this density of states. So for spin up, you shift to the right, and for spin down, you shift to the left. Okay. And this was measured by Meserve and Tero in 1970s. Okay. If you add spin relaxation, these peaks, they broaden a little bit, and then actually with very strong spin relaxation, you get rid of the double peak feature, and you get only, depending on whether it's spin orbit or spin flip, you either kill superconductivity or you just come back to the spinless situation. Okay, so this was the first task, 1960s and 70s physics. Okay, so now next what we want to do is that we want to describe basically the boundary conditions to our equations, which is basically studying the boundary between the ferromagnet here and the ferromagnetic superconductor, so to say, I mean, the superconductor carrying an exchange field. And basically we will do a tunneling model, because actually also in these experiments they had tunneling junctions. Okay, and in this case I will actually concentrate only on the Keldysh part of the Green's function. Also there are of course interesting boundary conditions for the spectral parts. But since I'm mostly interested in what happens to out-of-equilibrium things, I can forget about mostly about them. And actually, in our work, we mostly assume that the spectrum is the one of the bulk superconductor. Okay. So now I look at this Keldysh part, and sort of an added piece of information is basically that this Green's function squared should be unity. So, and this normalization condition is satisfied if the Keldysh part can be described by this kind of a choice. So you can easily check it by just plugging it in and using the normalization condition separately for GR and GA. Okay, and the thing that you add here is this F matrix, which is nothing but the distribution function matrix. Okay, describes the out-of-equilibrium distribution function. And it's also a 4x4 matrix, but it can be chosen to be of this form. So there are only a certain number of real parameters describing it. In this case, 8 in total. So you can choose it to have, let's say, the parts which are independent of spin, and then there is a spin-dependent part. This sums would be over J. Okay. And I will discuss the interpretation of the different parts of the distribution function a little bit later in my talk. But anyway, so what we first wanted was the boundary conditions. And this is actually how we approached it. We want to study now a boundary condition from a ferromagnet to a superconductor. And the ferromagnet is characterized by the spin polarization. Okay. And let's say, which is basically defined as the polarization of the conductance of this tunnel barrier per spin. Okay, so this is a strict definition in the normal state. This polarization can be encoded into a so-called tunneling matrix, where, okay, I forgot actually to define T and U, but basically the U describes the T and U describe the spin polarization here. Okay, and now the boundary condition is basically to equate so-called matrix currents, which are just consist of the different components of the distribution function on both sides of the barrier with a quantity like this, so which is obtained from from a commutator. Okay, so far it looks very formal. I will give you some physics in a moment. Okay, actually this boundary condition was given by Berzere, Verso, and Volkov in 2012. It was, I mean, the whole general boundary condition for an arbitrary interface was discussed by Matthias Eschwig, Cotte and Belzig and Linder in this paper. So this is a specific case, but I think specific case that still has a lot of physics in it. Okay, so you look at the Keldysh part, you write the different components of the distribution function, you get some matrices, and then sort of this is how it goes formally. I will tell you what it means in practice in a moment. Okay, and actually this is already the first kind of finding that we had in this, new finding that we had in this project. This is something that was then published 2014. Out of this work, there are also related works in these papers. And this is related with thermoelectric effects. So we found actually that this interface already is interesting because it supports very strong thermoelectric effects. Okay, so what are thermoelectric effects? Well, just a brief reminder. Let's assume that we have a contact between two reservoirs. Those reservoirs are held at potentials mu L and mu R, and temperatures TL and TR. So there is a temperature difference and voltage across this contact. Now, these two sort of biases lead to two currents, charge and heat current, and the response matrix is described by this form. So the diagonal part is the charge conductance and heat conductance, and then if you describe it properly, then you can show that the off-diagonal part has to be symmetric, and this is the thermoelectric coefficient, alpha. Now, this has been, of course, discussed a lot I mean, since 1830, basically, this thermoelectric coefficient. One of the things that you can do with it is to realize thermoelectric heat engines, where you convert heat to power, so heat to electric power. And the conversion is described by an efficiency, okay? And the maximum of the efficiency that you can get is obtained by the Carnot efficiency times a quantity which involves this factor called ZT, which is the thermoelectric figure of merit, which is defined this way. So it relates to this alpha here and the different conductances, okay? And you can show that if ZT becomes infinite, then actually you get a Carnot efficiency from your heat engine. Now, the question is basically to make very large ZTs. Actually, the maximum ZTs that one has obtained with semiconductors are around 2 and 3, which is not too good, actually, for heat engines. Okay, so you can do theory for those. So this is kind of a detour from superconductivity. I will come back to superconductivity in a moment. And the theory usually proceeds by just making, let's say, linear response from linearized Boltzmann equation. This is something that you have in, for example, in Ashcroft-Mermin. And you can, from there, calculate the different coefficients, basically the conductivity and the thermoelectric coefficient. And what you notice is that the thermoelectric coefficient can be written in this form as an integral over some quantity where you have the, let's say, the density of states, the diffusion constant, and energy. And what you notice is that so this part is even in energy. This is odd in energy. So this means that in order to have a finite alpha, you have to have an odd component in this. And this is not that easy in metals, because in metals typically these are almost constant, the density of states and the diffusion constant. Okay, which means that typical alpha in metals is actually 0. Okay, so this is actually what's called, what I did here was related to the Sommerfeld expansion that you have, you have, for example, described in Ashcroft-Mermin. Okay, which relates to this so-called Mott relation of our thermal power. Okay. Now, in metals, indeed, the typical magnitude of the thermoelectric effects is of the order of temperature divided by the Fermi energy, which, and this law basically comes from just assuming a quadratic dispersion and looking at the density of states for that. And basically this means that the thermoelectric coefficients, thermoelectric effects should be extremely weak in metals. So how about superconductors? Actually, first it was thought that superconductors don't have any thermoelectric effects. Nowadays it's known that they do have thermoelectric effects, but they are even smaller. So the typical estimate of thermoelectric coefficients in superconductors is that it's basically this metallic thermoelectric coefficient times some factor which basically counts the number of quasiparticles in the system. So this G is always smaller than 1. Okay. Now, so this means that basically if you want to have a large thermoelectric effect, you should rather use semiconductors and not metals. Okay, so I proceed a bit. I can, instead of the Boltzmann model, I can make a tunneling model for my currents. I basically get the same results. Okay. Now, and in this case, this alpha is given by just the sort of densities of states on both sides of the barrier. Okay, so requirement for large thermoelectric effects is strong energy dependence and electron-hole asymmetry, which basically means this odd component in the energy. Okay. Okay, so now let's go back to the superconductor ferromagnet systems after this detour. So in the ferromagnet, let's remember that we have this spin split Fermi, which leads to this spin polarized interface. Okay, so which basically translates in the fact that whatever we are measuring at the interface, we should weigh the spin up with a different weight than spin down. Okay, and then the other ingredient that I have here is this spin split density of states, where of the superconductor carrying a finite exchange field. Okay, so okay, let's look at this spin split density of states a bit closer. What we see is that the superconductor actually still knows where the zero is, because that's basically the chemical potential of the superconductor. What you see is that, for example, the spin up density of states, it has a very large electron-hole asymmetry, because now what you see is that the holes actually have a much, the density of states is much closer to zero than the electrons. Now the spin down is of course exactly the opposite, so that the spin averaged density of states is still electron hole symmetric. But now I told you that if you have a contact with the ferromagnet, you should not weigh them with the same weight. Okay, and this combination of these two effects leads to very strong thermoelectric effects. So now we can simply calculate it. And okay, and what we basically get is that the thermoelectric part of this matrix gets a prefactor of this P, which is the polarization of the contact. And then this alpha here is just related with the spin asymmetry of the density of states. Okay, so in this case we get strong energy dependence electron hole asymmetry. Okay. This actually is related to our theory now, looking at the different currents in this case. And what I just described to you is basically this block where connecting charge current and energy current together. There is actually a larger, the matrix is actually not 2 by 2, but it's 4 by 4, because you can also study spin current and spin energy currents. Okay, and the general structure is like this, where you actually only need to calculate 3 energy integrals. So one for the conductance, one for the thermal conductance, and one for the thermoelectric effects. And then you get the whole matrix by just putting the polarizations in different places and the alphas. Okay. Okay. Good. So you can actually, this is so simple theory. It's just tunneling model with a superconductor that you can actually do pretty good analytics. So basically, what you do is that you replace. Okay, you have always here this derivative of the Fermi function, which is 1 over hyperbolic cosine squared. You can replace it typically with an exponential in the case when you have gapped density of states, like in our case here. And then you can do sort of calculate these integrals completely analytically, and you get this these results. And in particular, what you notice is that since you have a gap dispersion, you have kind of Arrhenius-like results where you have always e to the minus delta over t in these expressions. Okay. Now, so this means that actually the thermoelectric current in our setup is finite, but it's small. Okay. But not the thermal power. Thermal power is something where you, instead of a current, what you measure is a voltage in an open circuit configuration where the current vanishes. And this is just the induced voltage divided by the temperature difference, and this is given by the ratio between this thermoelectric coefficient and the conductance. Okay. And in this case, you see actually that the exponentials cancel out. And the thermal power actually should be very large in these systems. In fact, it's not even of the order of unity, it actually diverges. And it diverges like 1 over the temperature in this case. Obviously, there are some effects that then limit this divergence at very low temperatures, but I will not go to them. Okay, you can also calculate the figure of merit in this case. And in the ideal case where you forget about all spurious effects such as electron-phonon coupling and so on, which should actually contribute to the heat conductance, this figure of merit goes at low temperatures, depends only on this spin polarization. Okay, and what you see is that this ZT, as the spin polarization goes towards 1, this ZT diverges. So you get the very large figure of merit, yeah, basically you should go towards Carnot efficiency. Good. There were lots of questions in the beginning and now nothing. Okay. Anyway. Okay, so this was a prediction actually that originated from looking at these boundary conditions. 2014. This was meanwhile measured by actually the same group, by Detlef Beckmann's group. What they had was basically they made this kind of a structure where they had aluminum, iron, and copper, and where they heated the copper island, and then which meant that they had a temperature difference across, let's say, this bar, and they measured they heated this iron part, and then they measured the current between the copper and aluminum. Yes, and what they basically found was a thermoelectric current, which then was, for example, a function of the applied exchange field. Okay, so obviously, if the exchange field is 0, this alpha should be 0 also in our case here. So if you put h to 0 in this expression, you get 0. Okay, yeah, so these circles here are what they measured for the current as a function of the applied magnetic field, which translates to exchange field, and the theory prediction is actually the red curve here. Okay, well, the discrepancy is not actually resulting from theory; it's rather the fact that they overestimated the temperature difference because some heat also leaked to the superconducting side. Okay, so it fits perfectly in there. Actually, I'm saying that only fit parameter is the polarization. Actually, this is not true. They separately measured the polarization already. Yes.
The role of magnetic field?
Okay, good. So I tried to point it out. Let's see. Let's look at this. Okay. So the role of the magnetic field is to generate now this exchange field in this setup. So if you don't have any magnetic field, then there is no exchange field inside the superconductor, and this means that there is no spin split density of states there either. Okay, which means that this difference here is 0. Okay, if you apply a magnetic field, then spin up density of states gets shifted to the right, and spin down density of states gets shifted to the left, and then you get the difference here.
So there the ferromagnet doesn't play a role.
The ferromagnet plays a role of a spin polarizer, not a role of the exchange field. So indeed, you need these two components. Both of them have to be present. Okay, thanks for the question.
So is it the effect of the density of states, or so the density of states like 1D density of states and the symmetry?
Yeah.
So I mean, altogether, it is important that it's the divergent density.
No, divergence is not important.
Not important.
no, no. I mean, to some of the details of these let's say, these facts, it kind of, you could also have just a constant density of states with a gap, but shifted.
And shifted. Yeah.
Yes, yes.
But how you can get it larger than, say, in a semiconductor, where you can very easily get the gap and
Okay. You mean the ZT? Okay. Excellent question. I will come back to that actually in a moment, because in semiconductors, if you would look at this ZT here, you'll also get very large values. The reason is the spurious contribution of the sort of, let's say, other heat conduction channels, which is usually the problem. I will come back to that. Okay, so now we got this large thermoelectric effects. We can ask what to do with it. Okay, so remember, thermoelectric effects are actually two different effects. So one is this upper part where you convert temperature differences to charge currents, which is power conversion, and the other one is the lower part where you convert voltage to heat currents. So you get heating and cooling. So of course heating is not that interesting, but cooling is interesting. Okay. In fact, the cooling in these systems is not that unheard of. Actually, you get cooling even when there is no exchange field, no ferromagnetism anywhere. Because, and this was studied especially by Jukka Pekola, already starting in the 90s, in this so-called NIS contacts, or let's say here it's an SINIS system, where you study the cooling power of a normal metal resulting from voltage bias across the system. Okay. And what one finds out that indeed, actually in this case, the electrons on this island can be cooled by actually quite a lot. I mean, typically you might start from a couple of hundred millikelvin, and you may cool like a fraction of 2 or even more the electron temperature. Okay. Now, in the presence of the exchange field, these cooling curves, they lose the symmetry. So what you can see here is that at linear response, nothing happens in this Sinis case. You actually have to apply a voltage of the order of the gap to see something here. Now, with spin splitting, you get some sort of this curves tilt. And you get something at linear response already, which is basically what I already discussed before. You can study, of course, the nonlinear response also in this case. And you could ask, for example, the question, well, can I cool the electrons more than in the SINIS case? Unfortunately, the answer is no, not really. I mean, okay, so these are the cooling curves of the normal metal, in this case as a function of voltage. Okay. Now, so the blue curve here is the case where there is no magnetism, where there is no effect of magnetism, and you cannot get really much better. You get the sort of lowest temperature at a lower voltage, which actually translates to a better efficiency, but otherwise it doesn't matter too much. Okay.
I beg your pardon.
Yes.
In this calculation of temperature, do you include any relaxation with the phonons? Or
Sure. Yeah. Yeah, the phonons are included. Yeah. Okay. Now, yeah, but now since you have this linear effect, the difference in this case is that you can also cool the superconductor. So in the regular case, you always just heat the superconductor. Actually, as you are cooling the normal metal, you are heating the superconductor even more, because you have to dissipate this power somewhere. In this case, actually, you can cool the superconductor. So there is a sort of finite cooling power, which is basically the positive part of this curve in the presence of this spin splitting field, which means that you can actually cool the superconductor to somewhat lower from the starting temperature. So this is kind of the case where you start from some, I don't know, in the case of aluminum, this would correspond to 300 millikelvin, and then you go to below 200 millikelvin in superconductor temperature. Okay. Yes, that's the cooling. The more interesting thing is the power conversion, because this is something that you cannot get without this ferromagnetism. And now what I have done here is actually to calculate this figure of merit in the presence of the spurious effects. So really taking the basically the spurious effects mean that you have extra heat conduction channels, except for the electronic one. Usually they are related with phonons. Typically they are related with the actual phonon conduction. Here I'm assuming actually that it's the electron-phonon coupling that is the extra heat conduction channel. And I just, okay, so there is a parameter describing this, and I have sort of taken a typical value of this parameter, which depends on details of the setup. But basically what you can get already for the case where, okay, this is not FNF, but there should be a superconductor, of course, somewhere. So this is, the island in this case is a normal, and you get ZT values which can reach sort of, let's say, I don't know, 7, 8 at some very optimal case with very high polarization of the interface. In the case of the superconducting island, the electron-phonon coupling is actually weakened by the fact that you have a gap in the dispersion. And in this case, you get even higher ZT values. So these are theoretical estimates. Nobody has measured these yet, but these are estimates based on realistic values of these parameters. Okay, so you get true, sort of truly efficient heat engine out of this. Okay, but heat engines, okay, at low temperatures, what can you do with them? I mean, maybe they are not that interesting because, I mean, you are not going to put them to your car because you need a dilution fridge next to this heat engine. Okay, but actually where you can use them is in detectors. Because, okay, there are several superconducting detectors which are based usually on measurement of the impedance of the sample. So let's say the first one is the transition edge sensor, where people measure changes in the resistance close to the critical temperature. Okay, and as you probably know, the transition edge sensors were used to study, for example, the inhomogeneity of the cosmic microwave background. And that's why we know about what we know about the origins of the universe. Now, yes. Okay. Now, what we are actually suggesting that one could use such superconductive ferromagnet systems to detection, but instead of measuring, let's say, resistance or inductance or whatever, you actually measure directly this thermoelectric current. And this is advantageous because you don't need extra biases, and this should be better in many respects. Now, I will not go to details of the, let's say, noise analysis of this and so on. We submitted the paper this morning on this topic, but you can see them in Risto Ajajärvi's poster today. Okay, so let's come back to our initial task. We still didn't solve the problem. So the third task was actually to find the kinetic equations inside the superconductor to describe what happens to the non-equilibrium state there, and to describe actually this initial experiment. And this is work that was published in 2015. Okay, so let's come back to this Keldysh-Green's function. We have to, and this distribution function here. Now the distribution function can be written in terms of these different modes, which are basically just the energy mode, charge mode, spin mode, and spin energy mode. Okay, and so this is nothing but kind of a spectral spin accumulation. Its energy integral would be spin accumulation, and this is something like spin energy accumulation. Okay. Yeah, this is a pictorial representation of this. If you have, okay, just show a reference picture. If you have Tinkham's book in chapter 10, you have this picture where Tinkham describes the even mode of non-equilibrium and odd mode of non-equilibrium. These are basically two of the modes. So the even mode is the so-called FL mode or heat mode, and the odd mode is the charge imbalance mode. And these are the, let's say, the diagonal modes here. Okay, but in the case of sort of when you include spin as a relevant variable, then you also have two additional modes, which are the spin energy mode and the spin mode. Okay, and now if you do kinetic equations, you have to describe all the four of them. Okay, and the kinetic equations also come from the Husserl equation. So basically, we just plug this Keldysh-Green's function into this Husserl equation, and we find out what are the equations. And these are basically the analogs of the Boltzmann equation for the superconducting case. And now these Boltzmann equations, actually there are 4 of them, which come in pairs. So there's one pair which couples charge and spin energy current, and one pair which couples energy and spin current. Okay, and and typically, so there are some diffusion terms coming from the first term in the Usala, and then there are some relaxation terms coming from here. Okay, and those relaxation terms are, for example, related with the spin flip scattering and so on. Relaxation terms are in Boltzmann equation. They are called collision integrals. Okay, so and actually what you see in this this system is kind of this structure where you have this charge and spin energy are always coupled, and the spin and energy are coupled. And basically, if you have an interface with non-zero spin polarization, then you can actually couple in the vertical direction, which leads to a coupling of them all. Okay, in this case. Actually, now, based on this analysis, we already know what happened in this first experiment. And I sort of schematically, I can tell what happens is that basically this injection here, where the injection voltage was above the superconducting gap, that's heated up this superconductor. Okay, and the heat sort of doesn't decay at low temperatures that fast, especially in superconductors. The inelastic scattering lengths are actually quite long. And this, so this meant that this superconductor was heated over a long distance, and then that created the temperature difference across this detector contact, and that temperature difference actually drove a thermoelectric current. And this was actually what was measured here. And therefore, the relaxation length that was measured here was not a spin flip relaxation length, but it was rather an inelastic scattering length. In fact, we don't fully understand why it was so short. So it should have been a little bit longer, actually. Yeah, but okay, by putting in, yes?
I mean, at least in the previous version of that experiment, there was a spin sensitivity to the response. I mean, it wasn't just a thermal EMF that was being measured. It was a magnetoresistance effect that was being measured. Is that consistent with this picture?
Yes, because basically to see this thermoelectric effect, you have to have this finite spin polarization of the injector, of the detector. What actually was then, there is still another experiment by Beckmann where they showed that actually the injector, of course, if you look at the exact symmetry of these curves, these are, by the way, I mean, probably the red curves are theory curves, and yes, and blue curves are the experimental curves. You can see that so it's mostly antisymmetric, these curves, but there is some symmetric component which actually relates to the real spin signal still in those setups. But mostly they are antisymmetric, and this symmetry of the signal actually basically tells you whether it's related with heat or spin injection.
Can I ask quickly, you present this as a fact, is this actually also the opinion of the experimentalists now? It's the interpretation of the experiment, or?
You can see these curves.
No, I'm just asking if...
The answer is yes.
They also say that it is...
No, the answer is no. I'll talk about it after.
So,
okay. The answer is okay. Yeah, okay. Yeah. So this is at least the interpretation of the
so it's one possible explanation.
So, okay. So we will probably hear after me the other interpretation. Okay. For me, this is pretty convincing, but anyway.
So it would be, the curves would have a different symmetry if it were spin flip?
If they would be spin signals, yes. Yeah, they would be symmetric in that case. And actually, you can see that actually they have a small sort of symmetric component also. The real issue is actually the shape of the curves, which is related with the inelastic scattering, and also this length scale of the inelastic scattering and how it scales with the magnetic field, which is still a little bit of a puzzle. But I think the origin of the signal is definitely this one, at least in the Karlsruhe experiments. Okay, maybe we see the opposite opinion after me. Okay. Okay, so I'm coming to the end of the talk. I would like to mention one puzzle where your feedback is appreciated. Now, it's related with the continuity equation or some sort. So we all know that if you have charge current, let's say that typically how you relate this is the continuity equation, of course, it has the conservation of charge, and then let's say the relevant quantity that you measure is related with potential. For the energy current, the relevant quantity typically is related with the temperature, and the conservation law is related with energy. For spin current, the typical thing is that you would write some dynamical equation of magnetization, such as Landau-Lifshitz-Gilbert equation, and the conservation law is for angular momentum. For spin energy current, which is basically the fourth component in our case, the conservation law somehow, in the case you would have a conservation law, it relates to both energy and angular momentum at the same time, but I don't really know actually what would be a quantity that responds to a spin energy current. So your suggestions would be welcome on this. Okay, so this is a concluding slide. I have showed you that if you combine superconductivity and magnetism, you get effects that sort of neither of these systems actually exhibit alone, like this huge thermoelectric effect. Actually, there's a rich set of non-equilibrium phenomena, and I did not study even close to all of them what have been studied. Yesterday, we heard about this absolute spin valve effect. There are other related effects like this giant spin-Seebeck effect. Actually, even without a spin polarized interface, this spin split superconductor sort of holds this spin-Seebeck effect, meaning that a temperature gradient drives a spin current. The spin-Hanle effect is strongly modified in superconductors. That's an interesting effect because it depends on the details of the spin relaxation. You can also have rectification of AC signals because of the spin splitting and so on. Okay, thank you for your attention.